In the early morning hours of March 2nd, 2026, engineers at the Aero Engine Corporation of China posted a short announcement on the company's official account, the kind of dry, technical update that normally would have vanished into the noise of Chinese industrial news within a day. This one didn't. The announcement confirmed that a massive new turbofan engine called the CJ-3000 had just completed a grueling 3,000-hour endurance test, the mechanical equivalent of running a fully loaded wide-body jet continuously for more than 4 months straight without stopping, and that during testing, the engine had produced a peak takeoff thrust exceeding 35 tons, more than 70,000 pounds of force. State media coverage that followed leaned hard into the drama, with one widely shared post describing the endurance run as equivalent to a fully loaded C939 passenger jet flying continuously through the eye of a typhoon for 125 days straight. A vivid, if characteristically hyperbolic, way of conveying just how demanding the test regimen actually was. Within hours, the announcement had been shared across Chinese social media with captions calling it a breakthrough capable of causing panic among European and American aviation giants. That claim, stripped of its nationalist flourish, was not entirely wrong. A thrust output above 35 tons places the CJ-2000 squarely in the same performance class as engines like the General Electric GEnx and the Rolls-Royce Trent 1000. The exact power plants currently strapped beneath the wings of the Boeing 787 Dreamliner and Airbus A330neo, two aircraft that together have defined long-haul commercial aviation for the better part of 2 decades. For the first time in the modern history of Chinese aviation, a domestically designed and domestically built engine had crossed into genuine wide-body territory, the single hardest technical barrier separating China from true independence in commercial aircraft manufacturing. This is the story of how China got here, why the engine matters so much more than the airplane it's meant to power, and why the entire program still has years of hard, unglamorous work standing between this test stand milestone and an actual passenger boarding a Chinese-built wide-body jet. To understand why a single engine test result generated this much attention, you first have to understand just how badly China has needed exactly this kind of breakthrough, and for how long. China's ambitions in commercial aviation trace back formally to May 11, 2008, when the state officially established the Commercial Aircraft Corporation of China, universally known by its acronym COMAC, headquartered in Shanghai and placed under the direct oversight of China's State Asset Supervision Authority. The mission was explicit from day one: to build large commercial passenger aircraft domestically, reduce China's total dependence on Boeing and Airbus, and eventually compete with both companies on the global stage. COMAC's first serious flagship effort, the C919 narrow-body jet, a direct rival to the Boeing 737 and Airbus A320, moved forward with the kind of fits and starts that have come to define nearly every major Chinese aerospace program. Production officially began in December 2011. The first physical prototype rolled out in November 2015. The aircraft's maiden flight, originally targeted for 2014, did not actually happen until May 5, 2017 at Shanghai's Pudong International Airport. Full type certification from China's own aviation regulator, the Civil Aviation Administration of China, did not arrive until September 29, 2022, a full 8 years behind the program's original schedule. The first production aircraft was delivered to China Eastern Airlines that December, and the C919 finally entered genuine commercial passenger service on May 28, 2023, nearly 15 years after COMAC itself was founded. Here's the detail that made the entire C919 achievement feel simultaneously impressive and hollow to industry analysts watching closely. Despite being marketed and celebrated across Chinese state media as proof of the country's aviation independence, the C919 is powered by CFM International LEAP 1C turbofan engines, the exact same engine family, built through a joint venture between America's GE Aerospace and France's Safran, that powers the latest generation of Boeing 737 MAX and Airbus A320neo aircraft flying for airlines across the entire planet. China had successfully built the airframe. It had not yet built the engine. And in modern commercial aviation, the engine is not simply one component among many. It is arguably the single most technologically demanding, most heavily protected, and most difficult piece of the entire aircraft to master, a field where only a small handful of companies worldwide, GE, Rolls-Royce, Pratt & Whitney, and the CFM joint venture, have ever successfully built and certified engines capable of powering large commercial jets. That gap has not gone unnoticed inside China's own aerospace establishment, and closing it has become one of the country's most heavily funded, most strategically prioritized industrial goals of the entire decade. The vulnerability created by that gap became starkly, uncomfortably real in 2025, when United States export controls temporarily suspended the supply of American-made engine components destined for Chinese aircraft programs. a move that sent a clear message to Beijing. Regardless of how quickly the restrictions were eventually eased or worked around, China's response was not subtle. The country's most recent 5-year National Economic Plan, approved in 2026, explicitly listed C919 production output and, critically, broader aerospace supply chain resilience as top national priorities, an unmistakable acknowledgement from the highest levels of Chinese government that depending on American and European engine suppliers for the aircraft meant to symbolize Chinese aviation independence was, in itself, a genuine strategic liability. If China's narrow-body jet program had already been forced to reckon with this vulnerability, the stakes attached to its next, far more ambitious aircraft would be even higher. The next aircraft is the C929, a genuine wide-body twin-aisle jet designed to carry roughly 280 passengers, positioned as a direct rival to the Airbus A330neo and the Boeing 787 Dreamliner, the workhorse jets currently used for long-haul international routes across the globe. The C929's history carries its own tangled, geopolitically complicated backstory. The program actually began in 2017 as a joint venture between COMAC and Russia's United Aircraft Corporation, initially designated the CR929, with a CR standing for China-Russia, envisioned as a genuinely shared effort with design work split evenly between engineering teams in Shanghai and Moscow. High-speed wind tunnel testing using a scaled fuselage model was completed at Russia's Central Aerohydrodynamic Institute by December 2019, and for a few years, the partnership appeared to be progressing, if slowly. But Russia's full-scale invasion of Ukraine in February 2022 and the sweeping international sanctions that followed fundamentally destabilized the arrangement. China quietly ended its reliance on Russia's proposed PD-35 engine for the aircraft, and over the following 2 years, the joint venture structure itself unraveled entirely, with Russia formally exiting the program. What emerged from that breakup was a fully restructured, entirely Chinese-led effort, officially rebranded simply as the C929, now developed solely under COMAC's own leadership, without any Russian design input or dependency whatsoever. Freed from its Russian entanglement, but still facing the same fundamental engine problem that had complicated the C919 program years earlier, COMAC pressed forward on 2 fronts simultaneously throughout 2025 and into 2026 on the airframe and systems side, and the program reached several genuine, verifiable milestones. In February 2026, at the Singapore Air Show, COMAC signed a letter of intent with Aviation Systems, a 50-50 joint venture between America's GE Aerospace and China's own Aviation Industry Corporation, to supply the C929's core avionics processing system, essentially the electronic brain that will handle flight management, navigation, and systems integration throughout the aircraft. Preliminary wind tunnel testing began around the same period, marking one of the first tangible steps in validating the aircraft's actual aerodynamic design rather than simply its conceptual specifications. Air China signed a preliminary agreement to serve as the aircraft's launch customer, a symbolically important step for any new commercial jet program, since a committed initial buyer signals genuine industry confidence rather than pure government subsidy chasing an abstract national goal. COMAC's stated targets, as of the program's current design phase, call for producing the aircraft's first complete fuselage section by September 2027, achieving domestic Chinese certification by 2032, and reaching genuine commercial passenger service sometime around 2035, a timeline that places the C929's actual entry into service nearly 2 full decades after COMAC itself was originally founded. But it was on the engine side of the program where the truly consequential breakthrough was unfolding, largely outside public view until that March 2026 announcement finally pulled back the curtain. The engine now specifically targeted to power the C929, known as the CJ-3000, sometimes referred to in earlier technical documentation by the alternate designation AEF-3500, has actually been in active development for well over a decade, developed by AECC Commercial Aircraft Engines, a specialized division of the state-run Aero Engine Corporation of China, based in Shanghai. Its core engine test article, designated the C2XC101, first achieved ignition back in 2020, reaching just over 100% of its designed rotational speed in that initial milestone test, an important early proof that the engine's fundamental architecture was sound, even at that comparatively early stage of development. The engine's overall design reflects genuinely modern turbofan engineering principles, featuring a dual rotor architecture and a high bypass ratio of roughly 12:1, configuration broadly comparable to the bypass ratios found on the newest generation of Western wide-body engines, since higher bypass ratios generally translate directly into better fuel efficiency and lower noise output during takeoff and cruise. The engine's fan diameter measures over 3 meters across, giving it an unmistakably massive physical footprint, befitting an engine class built specifically to move an aircraft weighing well over 230 tons at maximum takeoff weight. The numbers that emerged from the engine's testing program throughout 2025 and into early 2026 are genuinely striking when placed side by side with the established Western competition it is directly designed to challenge. Chinese state media, citing figures from AECC itself, claimed the CJ-3000 demonstrated fuel efficiency roughly 15% better than the GE9X engine currently flying on the Boeing 787, a figure that, if it holds up under the kind of rigorous independent third-party verification. International aviation regulators' demand before granting certification would represent a genuinely significant efficiency advantage in an industry where airlines routinely chase efficiency gains measured in mere single-digit percentages, precisely because fuel costs represent one of the largest ongoing operating expenses any commercial airline faces. The program has also highlighted advances in the materials science underpinning the engine's most demanding components, including single-crystal turbine blades, manufactured at a specialized facility in Jiangsu province, described as among the largest such blades produced anywhere in the world, engineered to withstand operating temperatures reaching roughly 1,600 degrees Celsius, temperatures hot enough to melt most conventional metal alloys outright, which is precisely why turbine blade materials science sits at the very cutting edge of what separates a handful of world-class engine manufacturers from every other aerospace company that has ever attempted to build a large commercial turbofan and failed. Chinese engineers also reported successfully reducing the manufacturing scrap rate on those turbine blades to roughly 7.8%, alongside using 3D printed combustion chamber components that reportedly reduced weight by around 12%, while extending expected component lifespan by 1.5 to 2 times compared to earlier, more conventionally manufactured designs. It is worth pausing here to note, with the same rigor any serious aviation analyst would apply, that a number of these specific performance claims, the 15% fuel efficiency advantage over the GE9X chief among them, currently originate primarily from Chinese state media and AECC's own public statements, rather than from independent, internationally verified testing conducted by neutral third-party regulators. That distinction matters enormously, and not as a dismissal of the genuine engineering achievement the 35.2-ton thrust test represents, but as an honest acknowledgement of exactly where this program currently sits in its development lifecycle. Achieving a specific peak thrust figure on a test stand while completing a multi-thousand-hour endurance run is an extraordinarily significant technical milestone, one that legitimately places the CJ-3000 in genuine wide-body performance territory for the very first time in Chinese aerospace history. But it remains meaningfully different from achieving full international Type 1 certification from bodies like the American Federal Aviation Administration or Europe's Aviation Safety Agency, certification processes that involve years of additional testing under far more rigorously independent scrutiny. Testing that scrutinizes not just peak performance under ideal conditions, but reliability, safety margins, and consistent performance across the entire operational envelope. An engine might encounter across decades of real-world airline service, including engine failures, bird strikes, extreme weather, and thousands of individual component interactions that a single endurance test, however grueling, cannot fully replicate. That caveat becomes especially important when placed against COMAC's own broader track record of ambitious announcements meeting considerably slower real-world execution. By the end of 2025, COMAC had delivered a combined total of just 41 aircraft across its entire product line, 15 C919 narrow-body jets, and 26 of the smaller C909 regional jets, well short of the roughly 75 C919 units the company had originally targeted for that same period. The company entered 2026 carrying a backlog exceeding 1,000 aircraft orders, an impressively large number on paper, but one concentrated almost entirely among Chinese state-owned airlines and domestic leasing companies rather than international carriers. And as of early 2026, COMAC had not yet delivered a single C919 to any airline operating outside mainland China, despite years of stated ambitions to eventually export the aircraft internationally. That pattern, genuine engineering progress consistently paired with delivery timelines that slip years behind their original targets, offers an important grounding context for interpreting the CJ-3000's genuinely impressive test results. The engine reaching 35 tons of thrust on a test stand in early 2026 is a real, independently observable technical fact. Whether that same engine will be powering a fully certified, internationally trusted commercial airliner carrying paying passengers on schedule by the mid-2030s remains a considerably more open question, one COMAC's own historical execution record gives genuine reason for measured skepticism about. The CJ-3000 does not exist in isolation. It is the larger of two sibling engine programs AECC has pursued simultaneously as part of China's broader push toward aerospace engine independence, and the smaller of the two offers a useful, sobering preview of exactly how long this kind of program can take, even when it stays entirely on track. The CJ-1000A, sometimes rendered as the Changjiang 1000A, referencing the Yangtze River in its official Chinese name, has been under development specifically to eventually replace the CFM LEAP 1C engines currently powering every single C919 narrow-body jet in commercial service. That program dates back even further than the CJ-3000, with its first prototype assembled in December 2017 and its first successful test cell run completed in Shanghai in May 2018, reaching a core rotational speed of 6,600 RPM in that initial milestone. Flight testing aboard a modified Xeon Y-20 military transport aircraft, used as a flying testbed, reportedly began around March 2023. Yet, as of early 2026, more than 8 years after that first prototype assembly and nearly 2 decades after the broader engine program's conceptual origins, the CJ-1000A still had not entered a single C919 aircraft in actual passenger service, with independent aviation analysts, including Mayur Patel of the Aviation Data Consultancy, OAG, projecting that Chinese certification and initial deliveries were likely to begin sometime in 2027 or 2028, with genuine mass production not expected until around 2030. American aviation journalist John Ostrower, who has covered the Chinese aerospace industry closely for years, noted as recently as May 2025 that public sightings of the CJ-1000A engine actually flying remained genuinely rare, even after flight testing had technically been underway for roughly 2 years, a small but telling detail suggesting the program's real-world testing tempo has moved considerably slower than official. Statements alone might imply, if the smaller, comparatively less technically demanding CJ-1000A has needed the better part of a decade to inch this close to entering revenue service, that timeline offers a genuinely useful, grounding benchmark for judging just how long the larger, far more complex CJ-2000 realistically needs before it can carry passengers commercially, regardless of how impressive any individual test stand thrust figure looks in isolation, into territory that remains, by the company's own admission, in the very earliest conceptual stages. Industry analysis reports from mid-2026 indicate that preliminary design work has quietly begun on an even larger aircraft, tentatively referred to within industry circles as the C939, described as a prospective quad-class long-haul jet positioned to eventually compete with aircraft like the Boeing 777 and Airbus A350 in the largest, most demanding segment of the entire commercial aviation market. It is important to be precise about exactly what that means at this stage, because a considerable amount of online content has significantly overstated the program's actual maturity. As of 2026, the C939 exists primarily as very early preliminary design work and analyst speculation rather than as a formally launched, publicly detailed aircraft program with confirmed specifications, a committed launch customer, or any announced timeline remotely close to production. It represents essentially an acknowledgement that COMAC's long-term strategic thinking extends beyond the C929 toward eventually challenging Boeing and Airbus across every major segment of the commercial aircraft market, narrow-body, wide-body, and eventually the largest long-haul category as well, rather than a concrete near-term engineering commitment. Given that the C929 itself, already years into active development with a committed launch, customer and a defined avionics supplier, is not expected to enter commercial service until roughly 2035, any aircraft positioned as its larger, even more technically demanding successor realistically sits considerably further out on the horizon, likely well into the 2040s at the earliest, a timeline that depends entirely on the C929 program itself first proving successful. To appreciate just how exclusive the club China is attempting to join actually is, it helps to look at exactly who currently populates it, and for how long they have held their position essentially unchallenged. Since the dawn of the modern wide-body jet age in the late 1960s and early 1970s, when aircraft like the Boeing 747 first made genuinely long-range, high-capacity commercial flight possible, the market for engines powerful enough to lift those aircraft off the ground has been dominated by a remarkably small, remarkably stable set of manufacturers, principally General Electric and its various joint ventures, Rolls-Royce of the United Kingdom, and Pratt & Whitney of the United States, alongside the CFM international partnership between GE and France's Safran that has come to dominate the narrow-body segment specifically. No new entrant from any country has successfully broken into that wide-body engine club in more than half a century of continuous commercial jet aviation, not for lack of trying, but because the combination of extreme material science demands, the sheer capital investment required, and the multi-decade testing and certification gauntlet involved has proven prohibitively difficult for every single nation and company that has previously attempted it. Japan, despite possessing world-class precision manufacturing capability across its broader industrial base, has never fielded an independent wide-body engine manufacturer of its own. Neither has South Korea nor India, nor any other rapidly industrializing economy of the past several decades. That specific decades-long track record of universal failure among ambitious challengers is precisely what makes China's CJ-3000 crossing the 35-ton thrust threshold, whatever caveats remain about full certification, worth taking seriously as a genuine inflection point rather than dismissing it as simply more state media bluster from a country that has, admittedly, produced plenty of that in the past. Is the strategic logic driving all of it? A logic Chinese industrial planners have stated plainly and repeatedly for well over a decade now. Commercial aviation manufacturing sits among a small handful of the most technologically demanding, most capital-intensive industries on Earth, one where genuine barriers to entry have kept the global wide-body engine market effectively locked among just 3 or 4 Western manufacturers for the past half-century, regardless of how many other nations have. Whether the CJ-3000 ultimately fulfills that strategic ambition, powering a genuinely competitive, internationally certified Chinese wide-body jet carrying passengers on routes across the globe sometime around 2035, or whether it instead follows the same pattern of repeated delay that has defined nearly every previous major Chinese aerospace program, including the C919 itself, remains to be seen, and will only be settled by years of additional testing, certification work, and ultimately, real-world operational performance that no test stand announcement, however impressive its headline thrust figure, can fully substitute for. Skeptics within the Western aviation industry have pointed out, reasonably, that peak thrust and endurance hours represent only a fraction of what full certification actually demands, and that China's own history of ambitious announcements, followed by years of quiet schedule slippage, gives every reason for measured caution rather than uncritical celebration. Chinese officials and state media, for their part, have shown little interest in that caution, framing each successive test milestone as further proof that the country's long march toward aerospace self-sufficiency is not merely proceeding, but accelerating. Both framings can be true at once. The engineering achievement represented by 35 tons of verified thrust on a Chinese-built wide-body class engine is real, significant, and historically unprecedented for the country. The gap between that achievement and an actual certified revenue-generating passenger service remains just as real and just as significant, and history strongly suggests it will not close quickly. What is genuinely, verifiably true, and what makes the March 2026 endurance test result worth taking seriously despite every reasonable caveat about COMAC's execution history, is that for the first time in the entire history of Chinese commercial aviation, an engine built entirely within China's own borders has crossed the specific, brutally difficult performance threshold, separating a narrow-body capable engine manufacturer from a genuine wide-body contender, closing a gap that had stood essentially unchallenged since the earliest days of the commercial jet age. The road from that test stand in Shanghai to an actual paying passenger boarding a Chinese-built wide-body jet almost certainly still runs another decade long, filled with exactly the kind of certification hurdles, safety validation, and real-world reliability testing that has slowed every previous Chinese aerospace milestone before it. But the specific technical wall that has kept China locked out of the world's most exclusive aerospace club for the better part of a century just got measurably, undeniably thinner.